So we'll take a simple example. Imagine we have a XY plane where X represents horizontal and Y represents vertical. And now we have a projectile which you project from the origin itself. Okay? This is how you project with some initial velocity u at an angle theta. This is the origin. So now the line of motion of this particle right now is passing through the origin. So what is the angular momentum of this particle right now? Area about O at t equals to 0 is how much? So what we check is MUD, right? Mass into velocity, momentum multiplied by the separation of the O with line of motion. And the answer is 0. Correct? Do you realize this?
Yes.
Now this particle will trace a trajectory something like this. And after some time you may be here. And therefore your velocity vector will change. Not only in magnitude but also in direction. You see your new velocity vector. And I'm saying this is the velocity vector is at t equals to t. And if I extend this line backward, we can see that the point O is having some separation, and therefore we cannot say the angular momentum will be 0 right now. So after some time t, the L0 O at t equals to t will have some value, and that value will be mvd, where d is this distance. Now this is difficult to calculate mvd, but there is a better way of calculating the same. We can join this point, and we know this is r vector, and the vector notation is very much known to us. So the angular momentum about O, we can write as m into r cross v vector. So the previous one is not very useful to us because finding the d is a difficult task, not an easy task. So knowing that L not equals to m into r cross v, the question is, can we find the r, can we find the v as a time function? So the answer is definitely yes. So we can find the r and we can find the v function, and the r you can write as xi plus yj, and the v we can also write as vxi plus vyj, and then this is pretty straightforward vector multiplication. So I cross I will be 0, so I cross j will be k. So we have x vy k cap, and y cross I will be minus k cap. So the in essence the answer is x vy minus y vx into k. And now we have the answer ready with us. So L naught as a numerical value is m multiplied by x coordinate as a function of time t, which you can write as u cos theta into t, and Vy we can write as u sine theta minus g. Minus y will be difficult for you, right? U sine theta t minus half gt square, and the Vx remains constant, which is u cos theta. And now you need to rearrange and probably solve this part. I hope you can do this part. So can someone simplify this part and tell me the final answer? And you can see clearly that the angular momentum is a time-dependent variable. So of course, as time will progress, it will keep on changing. Anyone getting the answer? I think you guys are not seeing.
So,
So the answer is mu cos theta. I think u cos theta is common in both cases, right? So we can take it common. And then we can multiply here. Ut sin theta minus gt square. And then here we have minus. Answer is mu g cos theta by 2. So this is the magnitude part. So mod of angular momentum as a function of time t. Mg, mg u cos theta t square by 2 is the angular momentum as a time function. Okay. So you may get this question. We'll see later on that how we can solve this question almost in one line without doing any of this calculation. So what is the alternative way of doing the same problem? So the method 2 is fairly useful in variety of situation, and we know that the torque about any point is equals to uh, r cross f, and the torque definition is nothing but the rate of change of angular momentum about the point. So in a way, if a body is experiencing any torque, then its angular momentum will change with respect to time, and therefore the dl naught you can write as tau d. So this we can do easily, and then we can find the change in angular momentum. So if you look at the same diagram, let me read over here. So when you throw something like this, after some time t, the particle may be here, as we discussed, traveling some distance along horizontal. And what do we know that the only force acting on the body is gravity while it is flying. So the torque about O is pretty easy to calculate the numerical value. It is mg into x, and therefore, so the direction is minus k cap all the time. So I can write the dl naught integration is mgx dt. When t is 0, we have realized that this was 0 because the line of motion was passing through origin. So after some time, it will have L naught value, and now it's time t. On the LHS, we have the L naught, but on the RHS, we have mg outside. And x we can write as a function of time t very easily. This is u cos t time to t from kinematics. So the horizontal component of velocity into time is the x displacement, and now we're done. The t dt integration is t square. Pardon? I don't know. So L naught is equals to this value. So there are always two ways to calculate the angular momentum. If you know the torque which is well defined, if you can see clearly what is the torque, it is good to go by the integration method. But if the torque is not visible to you, if you're not sure about the torque, then it's good to go by the definition of L itself. And we use both method depending on the given numerical. So you need to be smart enough to choose the right method for a given situation. So nevertheless, you'll get the answer by both methods. But yeah, the other one is really, really simple. Next. So imagine we are okay. No, I should let on. So now we have seen the angular momentum of particles. So now, I mean, we should take the angular momentum of the body. And now I would like to discuss angular momentum of a particular body with respect to some axis. Just like the torque I defined about the point and about an axis. A similar explanation will exist for the angular momentum as well. Now, what does it mean that to find the angular momentum about a given axis, you need to find angular momentum about a point on the axis and then take its component. So when I say angular momentum about an axis, it's again a component. It's a component in the given direction of axis. So axis is like the guiding direction in which we are looking for the value of angular momentum. So when I say find the angular momentum about an axis, then I'm saying that can you tell me the value of L in the direction of axis? So in a way, I'm asking for the component. So let me put the heading first. And derivation is pretty much same what we did in the torque scenario, if you remember. So let's say this is axis. So this may be a body, but we are looking for just of one particle, which is maybe part of a body. Let's this part, and we want to find the angular momentum of this particle about this axis. So as a traditional rule, it says that you cannot find the answer about the axis directly. So what you do is you choose some random point on the axis and then find the answer about this point. First of all, you need to find the answer about this point, and for that purpose, what we do is we take the plane which is perpendicular to the axis, and we assume the velocity to be in this direction. So I can do velocity. I can do velocity vector maybe along this tangent or maybe inside. This is more visible. And then we can join this point. Or I can do one thing. This point. Let me put the point here. So it is a good idea if I choose the particle is here. Yes. And its velocity vector is something like this. Or maybe that. This is it.
So is it tangential to the circle?
Yeah. So now what matter is the velocity component which is tangential to the circle. In a way, the velocity must be in a plane which is perpendicular to the axis. So you may have velocity component which is parallel to the axis, but that will never contribute in the angular momentum. That we'll see very soon. So let's say the particle is having velocity v and this is the r, and therefore I can extend this r vector notion. So we know we can see r vector, we can see v vector. So what is the what is the angular momentum about the O? So it's r cross p, which is rp sine theta. So what is r? R is r. What is p? P is mv. And what is theta? You know the angle between the r and v is 90 degrees. So this is what you need to realize. This is sine. And the answer will be the cross product. And we all know that cross product is always perpendicular to the plane of r and v vector. So it is something like this. So r cross p, or you can say L about O, will have this relation. So if I say this angle is theta, and because of the this angle is also 90, the other angle becomes 90 once. So the if I say this axis as something called z axis, this is what we call generally. Z doesn't mean z in, in a sense, you know what I'm just naming it. So the angular momentum about a point is okay, but the angular momentum about the axis is interesting, and that is how much L not sine theta, correct? So now if I join the center of the circle with the same point, I get another triangle, which is again a right angle triangle, luckily. And then if I say this radius as capital R, then the capital R is nothing but R. Now let's solve this using the two equations. We can say Lz equals to L naught, which is mvr into center, and then R center we can replace by mv capital R. So the angular momentum about angular momentum about an axis is mvr. Okay. and Lz was mvr, and you can see that what matter is the line of motion and its perpendicular separation with the axis. How far, in a way, the line of force earlier was there, and the line of force and the axis were skew lines. Now the line of motion and the axis will be skew lines. So line of motion and axis will be skew lines, and r is the separation between the two. R is the perpendicular distance between skew lines. And now, which kind of velocity will never produce the uh, angular momentum about the axis? So if the velocity is intersecting the axis, it will have zero angular momentum about the axis. And second is obviously if the velocity is parallel to the axis. So you should remember that if velocity vector is parallel to the axis, then L about the axis will be zero. If velocity vector, I should say, if line of motion intersects the given axis, then again the angular momentum will be zero because the r is zero now. So in both the cases, if you see the situation like this, so you can say clearly that there is no question of angular momentum about the axis, and you may argue why. So it's not very difficult to actually understand this later. So to understand this a better way, let me give you two questions here only. I will remove it. Imagine the velocity is like this, parallel to the axis. Now, if you apply the r cross v method in this case, so it turns out to be here. So r cross v, the L naught itself will be like this. And the problem is that if the L itself is perpendicular to L, I mean to the axis, then the component will be zero. Because if two vectors are mutually perpendicular, then they cannot have component here. So that is a simple idea that why we say so. So any component of velocity which is parallel to the axis will contribute nothing. So we always take the component which is in a plane perpendicular to the axis. So that is a core takeaway in this discussion, that angular momentum about an axis is basically, I'm just removing it not to confuse you. So what is the takeaway? So the takeaway is angular momentum of a particle. And remember that both the derivation is pertaining to the particle, and we haven't come across body derivation. Am I audible?
Yes, sir.
Okay. So anyway, PDF so far we have lost. So there will not be any PDF, but I think I have shared the rotational notes. No,
Yes.
Yes,
you
sir.
can see there. No, the network just got disconnected. I don't know why. Anyway, so the takeaway was that angular momentum about an axis is basically a component. So when I say the word axis, I always look for the component. So now we'll see something more deeper about the angular momentum, and we'll see how things works. So analysis of angular momentum for simple uh, for conical pendulum. So conical pendulum is something very famous, and by the analysis of conical pendulum, we actually understand some fundamental behavior of angular momentum. So let's see the axis about which a particle is making a circular motion. The particle is suspended using a thread. So let's name this as point of suspension as O and this point as Am I audible, guys?
Yes, sir.
Yes, sir.
Actually, I have switched the network from one Wi-Fi to other. Hopefully, this should not break. So, in the conical pendulum, let's say this is the axis, the line of symmetry for the pendulum, which is making the revolution around this axis. And technically, what is given to us is the omega and the length and the theta. So these are the parameters which is generally known to us. In fact, omega is also not required, but because we know that omega can be derived using the equilibrium of the bob in the non-inertial frame. So we have done this pseudo force equals to t cos theta t something like this, right? So omega, if you remember, the answer was omega was g by L cos theta. I hope you remember.
Yes, sir.
Okay. So today I'll try to derive this formula using something really tough method, which is really huge. I mean, really lengthy method. Okay, anyway. So we have this object, we have this everything, and now uh, if we talk about the force, then this is the energy. And the other force is tension force. We know that this is that these are two forces only available. And next is the path. So we have this path, and let's name it O, and let's name it Z axis. So now the velocity vector of this particle will be tangential, right? So it will
Yes.
be tangential at every point. So right now it will be towards you. So I can just draw the V vector like a dot sign because it is towards you. Yeah. So you have to imagine a vector pointing towards you, and that's the V vector. And I hope you can also see the L vector, correct?
Yes.
So let's say I'm trying to find the angular momentum about O. So definition says it's R cross P, which is RP sine theta. So we'll try to find what is R, what is P, and what is sine. So as of now, let's assume the velocity is V. We can of course write the V in terms of other variables, but let's say velocity is V, which is a variable, but the magnitude is constant. So V vector as a variable, but as a numerical value, it's fixed value. So we need to understand that if you are willing to find the L about O, then the O becomes the origin, and R vector is always away from the origin. So the way we write the R vector is like this. So how many of you realize that R vector is like this? And therefore, the R vector will, I can extend this R vector like this, in this particular fashion. This is the R vector. And the velocity vector is towards you right now at this particular instant of the diagram. Uh,
What are the
so now tell me, what is the theta? What is the angle between the R and P vector? Tell me, guys, what is the angle between R vector and the V vector? P means the velocity vector.
So velocity is towards us.
Yeah.
Sir, is it
So what,
perpendicular?
yeah, definitely it's perpendicular. So always remember in a cone, the tangent to the base and the slant are always perpendicular. So this turns out to be actually only RP, which is MVR. So the angular momentum about O is MVR because the velocity is the right angle to the R vector. So we need to multiply the momentum with R because in angular momentum calculation, if you remember, we always multiply the one value and other perpendicular value. So you either you multiply R with perpendicular component of MV or MV into perpendicular component of R. So it's other way around. So here things are very simple. The MV and the R are mutually perpendicular all the time. And therefore the modulus of LO is going to be same all the time. But can we say that the angular momentum about O is constant? Can we say LO vector is constant? Is it true or false? Is it true or false?
Sir, true.
No. So now knowing it's false, can you justify this? Why it is false?
Sir, because the direction of velocity uh, vector changes every.
Yeah. So if V vector will change the direction, then what will be the effect? So in fact, V vector and R vector both will change the direction because R will be like moving on the slant surface of cone, and V vector is translating. I mean, along this circle. So the L naught as a vector will keep on rotating, and how it will rotate it is very simple. You can visualize this. So right now, if I draw at a point O, the direction of L naught. So we know that for from the definition of cross product, the vector is always normal to the plane containing vector A and B, right? So here R and P. So by definition, so the direction of L will be normal to R and normal to P both. So what you can do right now is the R is visible to you. You just draw the normal to the R. But this is there are two possibilities. This could be like this or like this. So which one is true? The below or the above? So for that you need to use the right hand thumb rule R cross P, and you will realize that R cross P is this one. So this is something difficult for you to realize. If you realize, then your job is done.
Yeah, sir, understood.
So this is the direction of L naught vector, and as the particle will move, this L naught vector will start turning in this circle. You can see this is the circle. As the particle will traverse the circle, this L naught line will also traverse this circle. And you can see that the length will be same. So length is always going to be the same value, no matter what. this is exactly the path of the L naught, and that's why I said the L naught as a vector is not constant. It is constant only as a magnitude. And something very interesting you can see here, that what is the angular momentum about the z-axis. Let's say try to find the Lz, because we know LO. So this angle we know this is 91 theta, and therefore Lz will be how much? L naught sine theta, correct? And which is mvr into sine theta. And again, the r sine theta is nothing but this radius, which is the perpendicular separation between the velocity vector and the axis. That is what we know, and you can see the answer is still the same. I'm not sure. It is mvr. Now you can also realize something more deeper here. As the particle will travel, the L naught will sweep this slant surface of the smaller cone, as you can see. But the component will be same, isn't it? So no matter where you go, the Lz is not changing. So can we say Lz is constant? Can we say this?
Yes.
Is it true or is it false?
So
The
at
answer is
So true.
yeah. So even in vector form, it is true. Like if I say Lz direction also, this is constant.
So because it's zero or not is
Yeah, because there is no torque about the z-axis, so that is what we have to, of course, describe or analyze after this. So we are looking at one scenario, and then we'll try to correlate the two things: that the torque and the angular momentum. What is their relation? So the relation we have discussed in the beginning about the torque. Now today we know what is angular momentum. Not the two will merge together, and you will see that there is a one-to-one relation. Like they are related with each other in one way or the other. Okay. Now L naught is constant in value, but it is variable. So can you find the DL, the change in angular momentum in time dt? So this is another calculation which I want to put it here separately. Can we find DL naught? And what is DL naught in time dt? Now this is again purely mathematical stuff. So
can be so.
yeah, you can say. Okay. So I'll just do the topmost point. This is the L naught. And so this is the L naught right now. And after time dt, the vector will just swap a bit to the right, something like this. And this change,
Sorry, it's MGL sin theta dt.
pardon?
Sorry, is it
So this is
MGL sin theta dt?
MGL signed. Just let me check. Let me check this.
Yeah, sir. I'm
So
giving the same answer.
yeah, so this angle I can say as what do you say? So we are looking for this. The change is here. This is the change. So this is L naught. This is 90 minus theta. So what will be the radius vector? This vector is how much? The radius of this circle? It is L naught cos theta, right? So this radius, if I call the radius, this is the cone with L naught as a slant length. So I'm saying that L naught is the length of this slant of this cone, What is the radius of this cone? So radius of this cone will be
L naught cos theta.
L naught cos. And what I'm looking for is this change. So this if I say this as d theta, I mean no d phi. Let's call this angle as d phi angle. Then the dl naught will be the r radius into d phi. Correct. So dl naught we can attach because this is the dl naught, the change in angular momentum vector. So the dl naught we can attach L naught cos theta d phi. You can totally ignore this box. This box is for my own sake of teaching. I always teach it. I mean, of course. But you can ignore it. I mean, this is something really challenging calculation. So what I'm doing is something fundamental. So dl naught is L naught cos theta r d theta. Do you realize this? Okay, maybe
Yes,
so
sir.
now. So because we know L naught is constant in numerically, cos theta is constant numerically, d phi is variable. So if I write dl by dt, what I'll get is L naught cos theta d phi by d. Well, so d phi by dt is nothing but the omega. So our answer is L naught omega cos theta. Now from the definition of torque about O, it is due to the gravity, I think. So it's mg into L sin theta. Correct. I hope you know this answer. And then the third relation is the torque about O is dl naught by dt. This implies mgl sin theta is equals to L naught omega. What is L naught? L naught was mvr. Oh, mvl only, right? Because r is into omega into cos. So we can cancel m and l, right? And what we are left with? If ml gets cancelled, we have g sin theta equals to v omega cos theta. But what about v? What is the velocity vector? Velocity vector is omega into r, and r itself is L sin theta. So this becomes omega L sin theta into omega, which is omega square L sin theta cos theta, and this will cancel out. This will give you. Okay, I don't have space. I can write here. G equals to omega square L cos theta, and now you can see omega is G by L cos theta. Oh, very big derivation. This is a simple derivation. If you remember the circular motion, we have done this.
Yes, sir.
And now the same derivation I'm trying to do using the very basic definition of torque and angular momentum. So this box is just for some curious mind. If you are curious, you want to understand something more deeper, you should know this. If you don't care about it, you can ignore this. So most of the tough Theorem questions are based on this idea of writing angular momentum and torque. So any question which is very difficult can be solved using the basic way. You need to start with the definition, and from there, if you proceed, hopefully you will answer. Okay. So now this box you can go. I mean, this is not necessary for the sake of other examination. Okay, so v equals to so much of this is the derivation. So what is the takeaway from here? Now let's go back to the torque derivation. I told you the torque about the z-axis is 0, right? So Lz is constant, and if I differentiate this, it is going to be 0, and we know this is 0 because the torque about z was 0. It means the axis about the axis, the torque was 0. We have realized this earlier. and so the angular momentum must be constant, but the torque about the point O is non-zero. You can see, in fact, I have written here. This is the torque about the point which is non-zero. And because this is non-zero, so there is no question of conservation of angular momentum about O. So you cannot conserve the angular momentum about a point, but you can conserve about the axis. Okay. And what else? Okay, you can also talk about the point P. We have done this in past. So about point P, again, luckily both are conserved. Angular momentum is conserved, and why it is conserved? Because about point P, the torque is zero. Why torque is zero? Because mg and the tension will create equal torque about the point. Mg will create a mg capital R, and torque will tension will create T cos theta capital R. And because T cos theta is equal to mg from the equilibrium, therefore the net torque is again zero about point P. And because net torque is zero about point P, therefore again the same thing. Okay. Next. So this was the discussion on the torque part. Okay. So the other example was the hemispherical bowl example. And this is the line of simplicity of this uh, bowl, you can say. So what we are going to do here is we are going to throw some object parallel to the inner surface. So it means you may have some objects here, and what you do is you impart a tangential velocity to this particle along the surface. So the initial velocity is given along this circle, maybe like this, and this radius we can say maybe as small r, and the bigger radius is we can say capital R. Okay. So now again the same discussion will be ensue here also. So if you have realized the previous one, you can easily say what is going to happen here. So if I ask you what about the LZ and what about the LO, so which one is conserved, which one is not conserved? And which one is conserved? Which quantity will never change? Tell me which quantity will never change.
So once.
Sir, LZ will never change,
Yeah,
and L naught vector will change, but its magnitude will not change.
correct. And the similar analysis, the gravity and the normal reaction will create the similar situation as the tension was creating. And this will be one of the question that you will solve that we have to apply the conservation of angular momentum to solve question like what minimum velocity we must give to the particle so that it comes to the top of the ball. And you must have experienced this that if you throw it very fast, it will come out of the ball actually. So you can go to kitchen and take some small potato and throw inside a wok. You can see this experiment clearly. If you throw very fast, it will come out. And you need to just throw it horizontal, I mean tangentially horizontal. And this sometimes happens also in case of tornadoes also. So okay, so we had in my city something like a big table with a vortex kind of table was like this. Have you seen such table with a dent inside?
Yes, sir.
And you throw marble here, so it will round will go down. But after going down, it comes up. It goes down, it comes up. And why it comes up? Because when it goes down, the velocity will increase because of the loss of potential will convert into kinetic energy. And with that velocity, the normal will create a vertical component bigger than the weight itself. So if you move really fast in a circle, then the chance is that you may come up the circle very fast. So things like that was there, and at least if it is not enough, then you can see that the rate of going down will decrease. So it will first fall from bigger circle to small circle, but in a very small circle, it will make many rounds before going down. So in some science museum, maybe in Mumbai, you have the Nehru planetarium. You can see hopefully there. In my city, it was there. So we used to go in childhood there. When I was in class eighth, ninth, I used to go. And that time the ticket price was 50 paise. I don't know how much it is. Like so, this ball and this radius. I mean, we'll do the question of conservation of momentum. Now we should go to the next part. So we have done a lot about particle. Now the body is something we need to take care of. How to find the angular momentum of a body about a point, and of course we can do about an axis as well. So angular momentum of a body, and it is pretty simple because a body is nothing but a collection of particles, and therefore the answer is simple. You find for one particle and then you simply add all the other answers. So if we have a body, let's make our random body, and the body may be spinning on its own axis, so it may have some spin. Okay, so if I choose any point on the body, then it will have some r vector, and it may have some velocity vector, and the body is also moving somewhere else. So body is having VCM and omega both, so everything is there. So I choose some particles, I name it Mi, and let's say the position vector of the particle is Ri. Okay. And the velocity of this particle is Vi. So I'm just making everything I. Okay. So let me remove this axis. It will be more interesting. Right? So now the question is, what is the angular momentum of this ith particle? Just one particle. And answer is simple: mi ri cross vi. That's it. But we are looking for the body as a whole. So what is the total angular momentum? So we need to add all such values. So we need to add mi ri cross vi. So to get this answer, the net answer of the summation, if I add all values, what I'll get? That's the question, right? So we convert every value in the center mass frame. So we know that position vector of a particle with respect to its own center mass, we write as Ri minus Rc, and therefore Ri becomes Rc plus Rs. This is the first conversion. Similarly, velocity of the particle with respect to center mass, we write as Vic, which is Vi minus Vc, or Vc. I will just write Vc. And why I'm writing like this? Because Vic, if you take any point in a body and if you try to see the velocity of any other point, then it will be circular motion. So we can write as omega cross Rs. So this is from the velocity analysis, if you remember, which you don't anything. So Vi turns out to be Vc. Again, this part is totally for a mathematical purpose, nothing to do with the like remembering things. So even if you don't know this, it's totally okay. What you need to know is the end result, like how this will affect the end result, and what we must remember to solve the numerical. Okay. All right. So now this is the big calculation. Like we need to substitute this value and this value in the our expression, and we have to simplify this. So I will be doing this all this. No need to worry. You just see what is happening. So finally, L about O we got as M I R I was R C plus R I C cross V I was V I C plus V C, but I will further write as M I R C plus R I C omega cross R I C plus V C. I mean, there's so many terms to be multiplied. And then the first term will go with first term, RC cross omega cross RIC, and the second term is AMI RC cross BC, and third term is AMI RIC cross omega cross RIC, and the fourth term is AMI RIC cross VC. Now the summation mathematics, the sigma mathematics, if you know, only the coefficient, the variables remain inside the sigma, everything else we can put outside the sigma. So RC is without I coefficient, we can take it out. It's like constant, just like integration, if you remember. And then you can just write as AMI you can write like this. Similarly, here you can write summation of AMI, which is the only variable outside, and then rest, it's a scalar, we can just write like this. The third term is similar, AMI and the rest is outside. And the third term is again this. Oh no, this is something else. Here we have two terms, right? No, this is interesting. So everything will remain inside the. Okay, right now we cannot have a choice. Leave this part. This is interesting. This is interesting. No, this is not. This. The rest is of no use. Only these two terms will survive. Rest will die out. So plus this is again simple summation of AMI. Now there are certain things which you don't remember, which is difficult anyway to remember also. And what is difficult? This term is always zero. Anyone remember this from center mass?
Yes, sir.
Yeah, so this is called the first mass moment of a system of particle with respect to center mass, and this is always zero. Which means if you add all such values, it will give you zero answer because we are doing it from the center mass frame, and that's why the first and the last term will vanish. So what you're left with? The middle two terms, and this is pretty. This is the total mass of the body, m, and the second one requires some more calculation, which is like triple product. So in vector, I had given you formula, which I'm going to use directly. So A cross B cross C is basically A dot C all into B minus A dot B into C. And again, if you don't get it, it's totally okay. So what we are left with is and A dot A is A square. And this term is again 0. Why? Because the RIC and the omega will be mutually perpendicular. So omega is because we discussed about the plane motion. So in plane motion, we know that omega vector and the RIC vector. RIC will be in the plane and omega is normal to the plane. Therefore, the dot will be 0. So we also ignore this term. So we are left with only this term. And if you look even more carefully, the term here, what is this term representing? What is mr square? It's moment of inertia. But the r here we have taken from the center mass. So this is the moment of inertia about center mass. So this is ICM into omega. This is all by definition. This everything we have done from the fundamental definition in physics. And now you can clearly see that the angular momentum of a body is comprised of two terms. And you can see the first term is similar to what we learned in for a particle. So If you recall that what was the answer for the particle, it was something like this, right? M into R cross V. But the second term is something fresh. It is not new. This is something new. Well, this is something fresh. And if you realize something more, that RC and VC are frame dependent. So of course, if you change the frame, the first term will change, but the second term is ISM to omega. ISM is a fixed quantity, and omega is a property for body as a whole. And therefore, the two terms having some meaning, which we will try to explore. So now, as a student of any competition, you are supposed to know these two terms from that. So whether you understand the derivation or not, that's okay. But do you understand the two terms separate? L naught equals to the total mass into RC cross VC plus ICM into omega. This is the entire discussion of angular momentum. The first term, which is treating the body as a particle, and the particle is nothing but the center mass. So this we call orbital angular momentum. And the second is treating the body as a whole, not as a particle. And it is giving you the idea of the spin of the body, and therefore this is called spin angular momentum. Now, in case of particle, the second term is not possible. Only first term is the only answer. So for particle, there is only one term which gives you the answer. But for a body, the second term gives you the answer. Now the two terms convert into single term for variety of situation. So we'll see in which all cases we are not supposed to write the two terms separately. Only one term is sufficient. Let's see that. Now this is your the formula for this chapter. So what we can write? So the first thing is hinged bodies. If you have a body which is hinged, so let's take a random body. And as I hinge it here. So the body is able to turn about its hinge, and we will consider the motion as a plane motion. And the center mass is not there. Of course, center mass is somewhere below. Let's say center mass is here. This is center mass. And this length, let's call it RC. So the angular momentum about let's say omega is this body. So the angular momentum about an axis passing through O, we are taking the axis. Basically, we don't take about the point, we take about the axis mostly. So what is the angular momentum about this axis? This is what we are trying to find. It's simple. So what we can write? The first term, let's call it z axis. Always write as z. How to write? The first term, m r cross c. So r vector is below, and the vc will be like this, right? Now what is the angle between the rc and vc? It's clearly 90. We can just write rc vc. That's interesting. And what about the direction? rc cross vc will give you clockwise or anti-clockwise sense.
Anti-clockwise.
So this is anti-clockwise like this. And ICM omega, omega is anti-clockwise, so it is also anti-clockwise. No, it's confused. So omega is also anti-clockwise, so this is also ICM. So in a way, both because the sense are same, so we can just add. And for every hinge body, both sense will be always same. No need to worry. So I'm ignoring the arrow now. Now, if omega is the value, then how to write omega and VC relation? So we can write VC equals to omega into RC, circular motion, right? So because it's a rigid body, so every point will have circular motion. Therefore, the omega is sufficient to represent the velocity of that point. And now, if you look carefully, this is exactly the parallel axis theorem. ICM plus MRC whole square. And this is nothing but the angular. This is the moment of inertia about which point? O point. Or I can say IZ. It looks nice. Now, what does it mean that the two terms will become a single term, but the difference is the ICM omega will be changing to the IZ omega because the IZ is the new axis, and because it's performing pure rotational motion about the axis. So whenever we have an axis about which the body is performing pure rotational motion, in such case, to write the angular momentum as a sum of two terms, it is a good idea to write the angular momentum about the axis itself, which gives the sum of the two answers. And this relation is not present among teachers. So don't worry that if you have been taught wrong, even they don't realize that there are two types of angular momentum. I have asked many teachers, they don't know. So they have also mucked up that L is I omega. Anyway, that's their problem, not my problem. So you should remember that angular momentum is sum of the two terms, and you're not supposed to add both the terms and write the third term always. Only for some situation which I'm going to describe, you will be able to convert the two term into one term, but don't try to do it in every question in which you're not sure about. So now we know that angular momentum is Lz is Iz omega z. And now if you differentiate what we get is called the torque about the z axis is Iz into alpha z. This is the Newton's second law for such questions. So to solve the hinge body problem, you just take the torque about the hinge and write I about hinge into alpha. So again, no need to write the two terms in detail. So in what other case you can apply? In rotational dynamics, if you want to really apply these concepts, nowadays there is no question which is being asked, but all questions before 2000 in ITJ advanced, Like it was subjective question in that time. The rotation was the really challenge in that time. Now rotation question is not as difficult as it used to be. So from 1990 till 2000, the JE was asking the most difficult question from rotation. So now, okay, things are simple. Case two, or where these two terms becomes one term. So we know that if we have ICR, then what is ICR? ICR is a point about which body performs pure rotation, and therefore, if you know, let's say if it is pure rolling condition, for every question of pure rolling, the bottom act as ICR, instantaneous center of rotation. I hope you remember this.
Yes.
Yes.
And we also know that about this point, the bottom point, which I'm going bottom point. About this point, the omega and VC will have a relation. But let's say you don't know this relation. Let's say this is not a pure rolling motion. This is omega. This is, so what is the angular momentum about bottom? So we can see the R vector and the VC are mutually perpendicular. So we can write as what we can write? M R C V C, because it's simple. MVR. Basically, we can say MVR. That's it. Because these are mutually perpendicular. And the second term is ICM into omega. But again, you can see that L about ICR, because I'm replacing O by ICR. And VC we can write as, because it's pure rolling motion, so VC will become omega.
Omega R.
Oh, this RC itself is capital R, so let's write R omega ICM omega, and you know this answer. ICM plus MR square. Now, why we are able to convert these two answers? Because we know that it's a pure rolling motion, and that's why these two terms will again add up. And after adding up, this will give you what? The moment of inertia about bottom, correct? And therefore, if you differentiate this is the torque about ICR is I about ICR into alpha. The idea is simple. If you know the a given point is ICR, you can think that as a hinge. And once you know this is hinge, you just find the angular momentum and differentiate it to get the torque relation. Okay, so I'll tell you how to use this relation to solve question that we have solved previously. It is clear?
Yes, sir.
So there are two situations when we apply this. One when things are hinge, or something in which I can actually find the ICR, and if I know the ICR, then I can write the answer I omega. But I will become I about ICR into omega. So ICM omega and ICR omega are different things. ICM omega and I hinge omega is different things. So I not omega is not ICM omega. So writing the two terms, and imagine if there is no relation between V and omega, then the only way to proceed is writing the first method. So if VC and omega having no relation, then we start with this. We write this relation. Only when VC and omega having a relation, if you know that they are related to each other by the relation V equals to omega, you can blindly convert into formula I omega. So I hope you understand or realize that what is I omega. Okay. If you are confused in a situation when you have body and particle together, so you just write the answer separately for each part and add them. No need to worry about both. So this term you have to write as many times as many bodies we have, as many times as many particles we have. For particle, we write the first term only, if you remember. For body, we write the two terms. And with practice only, you will come to know, okay, what is required. Now, there are situations in which we have a body without spinning. In such case, the two terms will become only one term. So imagine if we have a cube. So we have a cube, and imagine this cube is translating only with velocity v0, and the side length is a, and inside is also. And now there is some bump or some obstacle. Now, if I ask you what is the angular momentum about O for this body, so how to start it? So you will start with the formula m v r cross vc, correct? And I is into omega. Do we have omega now? So is this body having omega? Tell me, is it spinning? Is this body spinning right now?
No, sir. So not spinning.
Yeah. So now that
Top by right.
there are two terms if you remember. And now my question is, which term we need to write here? So how we start with writing the angular momentum about any point? So we have to first think of the formula: mass into RC cross VC plus ICM omega, and the second term has nothing to do with the point taken. So this will and this term are independent. So O is the origin, and if you want, you can make it a line on this. So you can say this is R. That's it. So R cross V. So this is simple, no? Because the line of motion is clearly visible to us. So I will not go this much. And this is the distance of the line of motion and the O, right? So we can always replace this. What we need to know is the separation between the line of motion and the point of interest. And what is the perpendicular separation? What is this separation? Can you tell me? This separation is how much? Am I audible, guys?
Yes, sir.
So what is this separation?
A by 2.
And velocity is towards the right. So the angular momentum is clockwise or anti-clockwise? The angular momentum is clockwise or anti-clockwise? Tell me.
Clockwise.
Clockwise. So now what we can write here is the mass of the body, and what is the angular momentum value? So I can write m v naught into a by 2 clockwise. Correct? And the second term is 0. It is clear.
Yes.
Imagine we have a so we have a tortoise, and let's consider this is a hemisphere, solid hemisphere, and it's crawling on the floor, and the radius is r, and the velocity is v. So if I choose any point at the bottom, maybe here, what is the angular momentum of this tortoise about m is the mass? Tell me that.
So V is center of mass velocity.
V is velocity. Simply a body which is translating having velocity v. And I hope you know what is the meaning of translation. It's pure translation, right?
Yes.
So when I say v is the velocity, it means it's for every point is moving with velocity v, not just center mass, every other point. But when you write the first term, what you write? You write the position vector of center mass and velocity of center mass. So how the center mass is moving? So first of all, where is the center mass? Somewhere here.
Yes.
And what is the velocity of center mass? Same as the body, because the velocity is same. No? So what is this separation? This is 3r by 8. This will
Yeah.
be m
Yes.
v 3r by 8. It's not very difficult. Understood?
Yes. Sir.
Imagine after some time t, this cube reaches the obstacle, and the obstacle will prevent the motion of the bottom. So bottom cannot move further. Bottom is stopped. So what will happen to the body? If the bottom cannot go forward, what will happen?
Topple.
It will topple. So now it will spin about this axis. This will act as a hinge, because about this point, the entire body will spin. Understood? So if let's say if omega is the angular velocity, it will have just after hitting the this obstacle. Can you tell me what is the moment of inertia? Let's call it O. It's for the sake of writing. What is L naught L naught value right now? The
So
answer is
mass
simple.
M,
Pardon?
mass M, capital
Yeah,
M.
mass. Yeah, mass. The same cube. Just the same question. So once you hit it, the O point will act as a point of hinge, or because you cannot move from there. What happened? So what are you waiting for? Waiting for some miracle? Omega is given to you, so you have to write the two terms. How difficult is this to write it? So we know how to find the moment of inertia about central mass. We also know how to find the velocity if I know the omega. So what you are waiting for, I don't know what you are. If you cannot write the first two terms, then probably you cannot solve any question of angular momentum conservation in J mass. So you need to understand that you have to write two terms and you have to, yeah, somehow learn this method. So try this out. Anyone trying this question?
Omega m square by
Yes.
6 plus
Yeah, tell me.
sir, omega m square by 6 plus so one second.
Hmm.
Sir, is it 13 by 6 m square omega?
No.
Sir, is it omega ma square into root 2 plus 3 by 6 root 2?
No. So what is the first term? Tell me the first term first.
2 m square omega.
How much?
2 m square omega.
2 ma square omega is not the right answer.
Sir, is it m omega a square by 4 root 2? Means root 2 in numerator.
No. Tell me what is the velocity of center mass? Just after hitting the obstacle, what is its velocity? Tell me. So
Sir,
given the
omega
omega,
into
omega into
root 2 by 2a.
2 by 2, yeah, that's correct. A by root.
This.
So now you know the velocity of center mass and what is the RC, what is how far is the center mass from O?
A root 2 by 2.
A root 2 by why A root 2 by 2? It's root 2 A by 2, no? It's same thing. A by root 2.
Yes, A by root 2.
Yeah, sir.
So you know the RC, you know the VC. And what is the angle between these two?
45.
Okay, so here you go wrong. It's 90 degree.
Yes.
So here it is 90 degrees. So you can say it's a RC and VC is so simple. No? The answer is same. RC is also A by 2, A by root 2. And VC is omega into A by root. And the second term is ICM into omega. And ICM into omega is what? What is ICM? So we know the answer. AMA square by 6.
Yes.
And in fact, we could have written directly. So anyway, let's see the answer first. M omega A square by 2 actually. This is M. And if you add these two, what will get? M omega A square common 1 by 6. Let's say take 2 columns. 1 plus 1 by 3, which is 4
2
by
by
3.
3 ma square omega.
Correct.
So my first term was wrong. I took the diagonal length incorrect. I took
Yeah,
the diagonal length.
that is the common mistake made by 99.9% student. Don't worry. So you need to realize something like this. And the second was pretty straightforward because the O is the hinge. So no need to go through the two-way calculation. You can write directly I O omega. And that is exactly same answer. M square by 6 plus M square by 2. Done. So now only if you are sure that it's a hinge applies. And in case of confusion, always go through the basic method. Write the two terms separately. So when in doubt, write the two terms. If you are 100% sure that no, this is going to give me the same answer, apply that method. And now this is exactly the question of IIT that find the omega just after hitting the obstacle. And here what we are supposed to do is conserve the angular momentum about the hinge. And why we are saying you can conserve? Because when this block will hit the hinge will or the obstacle or the bump will apply the impulsive force, and the impulsive force cannot create torque about the same point where it is active. And in case of collision, we always choose those point as a conservation point which creates the impulsive forces. So hitting the bump is like a collision. It's a collision problem. And the rule of collision problem is simple. Just conserve the angular momentum about the point of impact. And why it is so? Because the point of impact will always behave as the origin of impulsive forces. And also remember that we have to conserve just before and just after. Why? Because other force will have torque, like gravity can create torque about O. So the idea is we should consider a small duration, like just before and just after, such that the torque developed by the gravity in small duration is negligible. I mean, the impulse is negligible. I'll talk about this in a while. So as of now, you are supposed to just remember one thing, that whenever we have a impact problem in rotational dynamics, you are supposed to conserve the momentum about the impact, and you're done. Your job is totally done. Understood? So what you can write is the answer. So we have the initial value before and after. So from conservation of angular momentum, and why we are conserving, I will explain further. You can just write mv naught a by 2, ignore the size of m, is 2 by 3 ma is for omega, ma cancels, and omega turns out to be 3 by 4 v naught by. A pretty simple question of j advance. So understanding the angular momentum is very, very crucial. Before I delve deeper into the angular momentum numericals, one thing which I left as an exercise in the Newton's laws of motion problem, which I told you that I can solve any question, or in fact we can solve any question in almost one line without writing anything, like no tension, no alpha, and so everything we can write. So let me demonstrate how to solve laws of motion problem using the angular momentum concept. So to begin with, I'll take a simple number, the inclined plane problem, and it is this method which makes sure that every question of eroda we can solve in one line. So this is the question of pure rolling motion, and we wanted to find the acceleration of this body, and it's a pure rolling question. Okay, so let's take a bottom. Just choose a bottom, or you can choose any point here on the plane. It doesn't matter. So the velocity and the omega are related or not related? Just tell me, are they related or yes or no? So do they have relation if it is pure rolling? Yes or no?
Yes, sir.
And if they are related, then bottom will act as ICF? Yes or no?
Yes, sir.
Find the net angular momentum about O. In fact, every point will have same answer. So the best way is to understand the bottom, and if you do so, the net angular momentum about O will be how much? Moment of inertia I about ICF into omega. That's it. Correct. Done. So dl naught by dt will be how much? Done. And now this term is easy to write. What do you can write? mk square plus r square, the parallel axis term. Is it okay? Done. Yes or no?
Yes.
And now what is the torque about O? So it is the gravity which can give torque. Mg sin theta will give torque because normal will not give torque. And mg cos theta will also not give you torque. So tell me what is the torque about O? It is mg sin theta into r, correct? And we are done. we got alpha g sine theta r upon. But we are looking for ACM, but we know this is simple thing, alpha r. So probably need to practice a bit to get familiar with such kind of method. So although I have written this thing, but mostly I can do this mentally because I know the torque is only possible is because of gravity about O. So let's see some more uh, interesting question that we did earlier. Now let's do it other way now. So I hope you remember the step pulley problem. Do you remember the step pulley problem? So we had
Yes, sir.
like three pulleys, which is like a hinge, and we have three threads. Let's say. Okay, I think this is too much for now, but okay. Uh, so let's say omega. You can mentally assume omega is clockwise, and let's say the radius is A, B, C. Increase, A is more. So their radii are A, B, and C. Just imagine. Now, if it is turning clockwise, let's assume, then how the M1 will move, up or down?
Up.
M1 goes up, correct. And what will be the velocity? Omega C. M2 goes up, velocity omega A. And M3 goes down. Okay, I've taken a bad value. So let's call it M1. This looks nice. M3. M2. So now M2 will go down, velocity will be omega B, correct? So about the hinge, what is the angular momentum for each particle? So what we do is we multiply the line of motion with the separation M1 VR, M2 VR, M3. It's opposite. No, sense wise, same sense. All will have clockwise sense. So all will add up. M3 omega B. Sorry, M3 omega C. So anyone getting this answer? Like this questions? Anyone getting the sense? Is this clear to anyone? I doubt.
No, sir. Not.
Yes, sir.
So what we are adding is MVR and O is the point, and the angular momentum for a particle, how we write? We write MVD, MUD. So you check the line of motion and check the distance, which is perpendicular distance from O. So can you check the distance? I think it's pretty much obvious. C, B, A. These are perpendicular separation, isn't it? From O to the line of motion of this block of masses, the point masses. I think you guys are not getting the idea of how to write the angular momentum of a particle. So if a particle is going this way and it's the point, we simply multiply this, no?
Yes, sir.
M,
Perpendicular.
and if this is idea is not coming to your brain, then you need to practice it. I mean, there's no way out. I cannot help much. And then what we do next is we just differentiate. And in a way, what I'm doing is we're just trying to write the omega as alpha. That's it. So this entire part we can do almost mentally, and this part we can do mentally anyway. So to turn clockwise, which gravity will create the torque? So we look for the external force and their torque. So the external force are M1G, M2G, M3G. So M2G will support into B, but M1G will oppose and M3G will also oppose. So this is the net torque equals to I into alpha, and we're done. So we got alpha. M2B minus M1A minus M3C into G. So now, once you practice enough these questions, you can almost start in your brain. This is totally you can do in brain. So you can spend some time realize what is happening. Are you able to realize what is happening here?
Yes.
Yes, sir.
Okay. Can you solve the question of Atwood machine? Oh, we made a mistake here. So we totally missed the angular momentum of the disc itself, the pulley itself.
So it will be alpha, right? In the third
Yeah,
and fourth.
yeah. Yeah. Okay, so now you can apply this concept here. So if you remember the Atwood machine problem, now that's pretty easy for you now. You have a pulley. The pulley will also have the moment of inertia that I totally missed. And then so we have two blocks attached to them. The radiuses are so let's say M2 goes down and M1 goes up. It doesn't matter. Let's say I think. And now it's easy to write. So which point what about which point we are going to write the angular momentum? The answer is center pulley. Now you may ask why? Because center pulley will create some unknown force which we don't. So we always choose the point about which some unknown forces are passing, such that the torque becomes zero for those unknown values, which I don't know. Now tell me the answer. What is L naught? So you can assume omega and the same fashion. This will go down with omega r. This will go up with omega r. and both will add up. The angular momentum will add up because both will have same sense. And the angular momentum of the this disk or this pulley we must write. So let's say the moment of inertia is given I. So not tell me what is L naught. It's not very difficult. Tell me guys.
Sir, it is omega into m1 r square plus m2 r square plus n.
Again, same mistake. Into R square plus I, right?
Yes, sir.
Into omega.
Yeah, into omega.
And now torque is simple. No? M2G, M1G. So talk about O will be how much? M2G minus I2R minus M1G minus I2R. So this is the torque. I'm differentiating in my mind only now. And so the answer will be M1 plus M2 whole into R square plus I into alpha, right? Done. M2 minus M1 into GR is M1 plus M2 into R square plus I into alpha. So you can multiply with R both sides to get the A acceleration of the block. So this is easy to find. And now we're done. So we got the acceleration of block equals to how much? M2 minus M1 into G. And yeah, you can just write M2 plus M1 plus I by R square. And this answer is very famous. We know this answer. Okay. So now what you can do is you can go back to all the pulleys problem mostly. And instead of writing the torque, you try to write the angular momentum and then just write the torque of the external force. And you will be able to solve any question of with much ease than before. And the benefit of this is like we are not supposed to write so many equations. So most of things can be done mentally. But this method is difficult to crack. So as a beginner, if you try to attempt this method, it will not be very intuitive what is happening. So in a way, you need to spend some time, some days with this method, and probably your brain can uh, consume or digest this. And once you digest, then you will be really fast in rotational dynamics. You can solve any question as quick as possible. So let me just solve some of the challenging problems, like one or two challenging problems, just to give you the sense of that there is no question in rotation which is challenging. That's the only sense I'm trying to say. So uh, now when we should not apply this method, of course, you should not apply this method when the torque is variable. So if you remember that in this case, torque is always the same, no matter where the block goes, torque remains same. In this case, where the block goes, no matter the torque remains same. So this, no matter where the body goes, the torque remains same. So these are the questions in which the torque remains same. And because torque is a constant value, so we are applying. So if the torque is not constant, you should not think of applying. Okay. So maybe we can take a bobbin problem. and small r, this is capital R. And the force applied is with the help of a string. So this is the force applied. And the angle meant by this with horizontal is alpha. The mass of the bobbin is m, the moment of inertia is I about center mass. So by default, when I say I, it's ICM. Okay. Okay. So now, okay, is this tangent? Okay. And now we are supposed to find what? The acceleration of this bobbin. Find A. And it's pretty easy. You know what is pretty easy? This is the challenging problem of Erodot. But I will solve in one line. Exactly one line, not two lines. So how to do this in one line? Extend this line. This is basically a tangent. Doesn't look like, but and because it's a again it's a pure rolling question, so the things I mentioned pure rolling and all. So bottom is not slipping, so I know bottom is my ICR. So this is something unset. So I know this is my ICR. So I'm supposed to find the so the angular momentum about O is pretty easy. I can just write I omega because I know this since for a long time. And I naught will be M or ICM plus M R square, which is capital R. Yeah. That. So I know the differentiation about O is I plus MR square into alpha. That's it. So I know this answer mentally. Okay, so for you, you can say, sir, there are two lines. No, this is for you two lines. This you can do mentally. Now the only question is what is the torque about O? So the about O, the normal cannot create torque, the gravity cannot create torque because all will pass through O. Only the F will create the torque, and the torque is this much. So let me make it a bit better. So now what we can do is we can just drop a perpendicular like this. Not very nice diagram. And once you draw the perpendicular, this is the simple. If I say this is D, the torque is FD. That's it. So this is the D. And now question is how to find the D. So finding D is again a geometrical problem. So if this is alpha given to you, you will realize this is also alpha. You can find it out. And because this is alpha, this is smaller. So now it's pure geometry. So let me do this geometry separately. So let me make it a separate diagram for better understanding. Maybe this is center mass. This is R. This is D. So this terms quite different on terms of scaling, but that's okay. So now the question is, if this is R, can we find this value? Because this is alpha, and it turns out to be this is R by cos alpha. And if that is the case, then what is this length? Because the full value is R. And because that is alpha, this is also alpha. Correct? And now we are finding D. So D is nothing but the, and so the answer is R cos alpha minus R. So I'm done. F into R cos alpha minus R equals to I plus M R square. We got the answer for alpha. In the question, what they had mentioned in the period that I is equals to ISM equals to gamma MR square, something like this. So things were, if you put gamma, it looks like gamma plus 1 into MR square alpha, then you got alpha into R. Okay, you can just say alpha equals to A of the body. So alpha is equals to F R cos alpha minus R upon M down plus. This is the expression of the centroids. So any question you can do by this method, you just need to practice a lot actually. So you solve a question by basic method, then try to think this way. The day you will get one correct answer, you will get the confidence, okay, I can do it. Right now it's difficult. I really understand. This is not so easy. So it is easier said than done. Like if I'm doing it, I know you're not getting exactly what is happening here. So it takes some time. Anyway, so the laws of motion part, uh, you can explore on your own. So maybe one last question. Okay. So this is the rod which is hinged at the middle point. The mass of the rod is m, length is m, and from the other two ends we have two block of masses suspended from the stick. So these are the point masses or just masses, and we are supposed to find the alpha of the rod just after it is released from rest. So we are trying to release from rest. So this is, and you may call this as m2 is more than. So the alpha of this instant we have to find, only this instant, not any other instant. So I hope you can see the torque about O. So torque about O is how much? What is torque about O? Tell me.
M2 L by 2
Yeah, M12 by 2
minus M1 L by
minus M1.
2. L by 2.
So plus
I mean,
M1 and
I'm asking torque. What is torque of external force on the rod? I mean the system.
so
So we have
M2G
three masses.
minus M1G.
So we do have some the reaction hinge force also. But what about O? These all torque will be zero of Ry mg. Only m1 m2 will work. So it is definitely m2 g L by 2 minus
M1 G.
yeah. Now to write the angular momentum, you can instead of alpha, you can choose omega to think. So what is the angular momentum about O? So for the rod, it's simple. Ml square by 12 into omega about center mass. For M1, M2, because their velocity will be omega L by 2, so it will be M1 plus M2. I'm writing directly into omega MV R. That's it. So the LO becomes ML square upon 12 plus M1 plus M2 into L square by 4 whole into omega, and therefore the differentiation, the torque will be alpha. That's just change the omega into alpha. And then you equate it. Okay. So you got the okay. Whatever you want, you can get the answer. Understood? All right. So you can solve questions like this. So now we have this question. This is the pure rolling question again, and we are supposed to find the accession of the block, or maybe accession of the center. Fine. So what is the accession of cylinder? So here we cannot apply the method that we learned. The to talk about, because we have many contact points. You can see we have here also hinge, we also have here hinge. So we cannot apply the two hinge problem. The hinge must be only one, and that is why we have to cut this from here and we have to solve this separately and this separately. Now solving the second part is very easy because the first part is the only question we need to solve. You can solve this part separately by finding the torque about ICR directly. So I can add. So torque about ICR is how much? T into 2R, and this equals to moment of inertia about the bottom, which is 3 by 2 mr square into alpha dash, and we are done. R cancel. T turns out to be 3 by 4 m alpha, and alpha is nothing but the acceleration of center mass. So we are done. Now write for block. For block, it will go down. Mg minus T equals to mass into acceleration, which is 2a, because that's the acceleration of the topmost point, and because it is connected to the topmost point, so the acceleration of this point will be same for the block. And see, it's pretty easy now. Okay, so the question like this can also come. So what I'm showing you all the ways of thinking and solving questions, and you should not take one method for granted. So there are methods in which this is not applicable as well, and so is a clear-cut demonstration of the same. Okay, so I think we are done with the laws of motion with the method of angular momentum. We have seen that how to write the angular momentum. So you should. We will be doing a lot of questions in the next lecture. Is completely dedicated for the angular momentum. In fact, the next two lecture will be of angular momentum only, and the last lecture will be the third lecture, energy conservation, which is pretty easy. There's nothing much to do, and that will be the end of the rotational dynamics. So hopefully by next week we should finish this rotational dynamics. This is a huge chapter, and however fast I may do, it will be always slow enough. All right, guys. Just a moment. Let me take the attendance. All right. Now you can leave.